In the same way that your cardiac output was the amount of blood that your heart pumped out your aorta per minute, your ventilation rate is the amount of air that you bring into your lungs each minute. And your cardiac output was a function of heart rate and stroke volume. Right? Similarly, your ventilation rate is a function of respiratory rate, how many breaths you're taking per minute, and tidal volume, how much air each breath includes in it. So pulmonary ventilation rate is your respiratory rate times your tidal volume. Right? But that pulmonary ventilation is not the same as alveolar ventilation because a lot of your lungs is full of dead space, essentially places that are not part of your respiratory zone, they're part of your conducting zone, and so there are no alveoli. You can't do any exchanging of gases there. So you have to subtract out what's called the anatomic dead space, meaning that the part of your lungs that's conducting zone, in order to figure out how much sort of functional ventilation you have, or alveolar ventilation. And so at rest, your anatomic dead space is about 150 milliliters. So if you're a typical tidal volume is about 500 milliliters of air, and if 150 of that is dead space, then we're looking at 350 milliliters left. And if you multiply that by breaths per minute, say 12 to 15, that gives you your alveolar ventilation rate. To show it in a relatively crude animation, right, this stuff here in your alveoli and your alveolar sacs can be exchanged with your blood, and so this counts. This is your alveolar ventilation rate, right? This is your dead space here, the conducting portion, where there are no alveoli. So we've already been talking about one gas law, Boyle's law, which is what states that volume and pressure are inversely correlated. So as you decrease volume, you increase pressure. And as you increase volume, you decrease pressure. And things always move, gases and fluids, from an area of high pressure to an area of low pressure. But I want to introduce another law called Dalton's law. And this has to do with partial pressure. So partial pressure is the pressure exerted by a single gas in a mixture. Because your atmosphere, our atmosphere, is a mixture of a bunch of different gases. It's mostly nitrogen, to be honest, but there's also a lot of oxygen, a fair amount of water vapor, CO2, things like that. And all of those together contribute to the pressure. And you can think of pressure almost like weight, right? So when you're jumping into a pool, when you go deep down in the pool, the pressure is higher. It hurts your ears. You don't get that same amount of pressure further up in the pool. But the reason you get that pressure down in the pool when you're deep is that you have a lot of weight of water pushing on you. Water is heavy. If you've ever carried a bucket of water, you know this. If you've ever Jack and Jilled it up a hill, you know that water has some weight to it. And so when you're under a lot of it, right, if you're at the bottom of the ocean, for instance, right, enormous pressures. And each gas in our atmosphere also contributes to pressure, right? It's very light compared to water, so you can't feel it as well, but there is pressure. And that pressure is made up primarily of these four gases: nitrogen, oxygen, CO2, and water vapor. And if you add up the partial pressure of all of them, it equals 760, which is the total atmospheric pressure. And if you look at inhaled air, so this is just what comes from the atmosphere, it's 78.6% nitrogen. So if you take 78.6% times 760, you get 597, right? It's about 21% oxygen, 0.04% CO2, and 0.5% water vapor. Now, as you move that into your alveoli, it's actually going to become higher CO2 and lower oxygen, higher water vapor, because it's been moisturized in your nasal cavity, and it's been mixed with air that's been sitting in your alveoli for a while, allowing for diffusion to happen. So CO2 coming in from your blood and oxygen going back out. So that's what that looks like. And then as you breathe it back out again, it starts to mix with atmospheric air again, and the oxygen goes up and the CO2 goes down. But while it's in your alveoli and diffusion is happening, your oxygen levels in your alveoli are going to go down because their oxygen is going to diffuse into your blood, where you have relatively low oxygen, and CO2 is going to do the opposite. So here you can see what's happening in your alveoli, right? You have a partial pressure of oxygen that, let's say, 100, And in your returning blood, so deoxygenated blood, your partial pressure of oxygen is like 40. We say deoxygenated, it just has lower oxygen levels. That's the partial pressure, but we can treat this kind of like how you treat concentration in terms of diffusion. So diffusion is going to occur from an area of higher partial pressure to an area of lower partial pressure. So oxygen is going to diffuse from the alveoli into this capillary blood here. CO2, which is about 45 partial pressure in the capillaries of the returning blood, about 40 in the alveoli, is going to move back. And this is going to change both the concentration of each of these in the alveoli and also in the blood. So by the time the capillaries pass by, your partial pressure of oxygen is going to end up going up, even though it doesn't show that here. So once that blood goes back to the left side of your heart and then gets pumped out of your heart into your systemic arteries, it's got much higher partial pressure of oxygen, right? About 95. And that goes to your tissues. And the partial pressure of oxygen in your tissues is going to be about 40, maybe even lower, right? Because oxygen, this is an oxygen sink. Oxygen is consistently being used up here. So as you add more oxygen to your tissues, it's going to get sucked up and utilized for cellular respiration and turned into water, right? So the diffusion gradient essentially is going to go from the capillaries into your interstitial fluid and then into your cells. Now you're constantly producing more CO2 at your tissues because it's a waste product of cellular respiration. So your partial pressure of CO2 is going to keep going up here. It's typically about 45, but again, if you know, it could be higher if you're not getting rid of it. And your partial pressure is about 40 in your blood, so CO2 is going to move this way. Now the partial pressure difference in oxygen is much bigger than the difference in CO2, which is going to make oxygen diffuse faster. But CO2 is better at dissolving in water than oxygen, and so that's going to make CO2 diffuse faster. So it sort of balances out. Now, because oxygen is O2, right? It's not just one oxygen molecule. It travels around as a molecule of O2, two oxygen atoms together. They're held together by a covalent bond that is nonpolar because each oxygen pulls on electrons at the same level of intensity, the same electronegativity. So this is a nonpolar bond, and that means it does not dissolve in water very well, just like fats, lipids, right? So that doesn't mean it doesn't dissolve at all, but very, very little. So only about 1.5% of the oxygen that moves through your blood is actually dissolved in your blood plasma. You can't survive like that, right? So you need the rest, the 98.5% that is not going to be able to dissolve in your blood plasma, to be able to move through your blood somehow. And so we have a molecule called hemoglobin, which we've discussed before. Hemoglobin, which has 4 different proteins in it, each of which has a heme unit in it with an iron molecule that is able to bind a molecule of oxygen. And when that hemoglobin molecule is bound to oxygen, we call it oxyhemoglobin. It likes to bind to oxygen. It's very good at it. That said, there's actually a molecule that has a greater affinity for hemoglobin than oxygen, or hemoglobin has a greater affinity for it, and that's carbon monoxide. This is why carbon monoxide is dangerous, because it takes up those binding places in hemoglobin, and it means that you're not able to move oxygen throughout your body effectively. And this is your public service announcement to make sure that you have carbon monoxide detectors in your home, especially if you have kids sleeping. And the more oxygen that's around, the higher the partial pressure of oxygen, the higher the amount of oxyhemoglobin you're going to have, right? The more of your hemoglobin is going to be oxyhemoglobin. And so this is a hemoglobin saturation curve. So as you can see, as the partial pressure of oxygen goes up, the saturation of hemoglobin goes up, the more oxyhemoglobin you have, until it begins to slow down up here. So this down here is your partial pressure of oxygen in active muscle tissue, right? It's very low. It's because you're sucking up all that oxygen. Up here, it's partial pressure of oxygen leaving peripheral tissues, right, in your blood. So this is your deoxygenated blood. This is your oxygenated blood. So this is the difference between deoxygenated and oxygenated blood. And this is going to be, again, tissues that are really cranking through oxygen, using it up to make ATP. Now this makes it easier for oxygen to diffuse from your blood to the places that need it the most, right? So if I'm doing some curls with my left arm, right? Got my coffee, doing my coffee curls, but the rest of my body's relaxed, right? I'm going to be using a lot more oxygen right here. And so diffusion happens at a greater rate when there's a greater difference in concentration, or in this case, partial pressure. And so more of my oxygen is going to stop here than is going to stop over here at the bicep that I'm not really using, right? So that concentration difference matters. But it's not just concentration difference that matters in terms of how we drop off oxygen where it's needed. Hemoglobin is also less good at holding on to oxygen in more acidic environments. So these are your hemoglobin saturation curves typically at your normal pH. Up here is at a slightly alkaline pH, and here is at a slightly acidic pH. Well, as I am cranking through oxygen here, I'm also producing CO2, because CO2 is a product of cellular respiration. And CO2 plus H2O, which I have plenty of in my tissue fluid, CO2 plus H2O makes H2CO3, which is carbonic acid. So as you put more CO2 into a system, it gets more acidic, at least in an aqueous system with water. And so where I'm using more oxygen, I'm producing more CO2, it's becoming more acidic. And so when hemoglobin gets to this spot, the pH drops, it gets more acidic, and the hemoglobin drops all this oxygen, right, and allows it to diffuse across. And so that's another way that we are better at getting oxygen to the places it needs to get, rather than the places where we're not using quite as much of it. And lastly, hemoglobin is not as good at holding oxygen as the temperature increases. It's better at a colder temperature. So 37 degrees is about your body's temperature, 38. If I'm doing curls over here, it's not just going to be more acidic and lower in oxygen level, it's also going to be warmer, right? We know that we produce heat as a byproduct of cellular respiration. When you go for a jog, your body heats up. You know this intuitively. But really, it's the tissue that's using the oxygen that heats up. And so when the blood gets there, it gets warmer. That hemoglobin drops a lot of its oxygen. It's able to diffuse across the capillaries into the tissue fluid and into the cells. So we've transported oxygen from your lungs to your tissue fluids and those cells. Now we need to transport the CO2 from the tissue fluids back to the lungs. And your blood does that as well. And whereas oxygen is almost entirely unable to be dissolved in your blood plasma, about 1.5% of it, almost entirely delivered by hemoglobin in the red blood cells. CO2 is a little bit more able to be dissolved in water. Right? It's not quite as nonpolar. It's a little bit better at dissolving. So about 7% of your CO2 is just transported in the blood plasma dissolved. Another almost quarter of it is transported bound to hemoglobin in your red blood cells. Hemoglobin can bind to CO2 as well, although not quite as effectively as oxygen. So a little bit of it's bound to your red blood cells. But the vast majority of your carbon dioxide travels as carbonic acid or bicarbonate. So as I mentioned before, CO2 plus H2O becomes H2CO3, or carbonic acid. Carbonic acid then loses a hydrogen molecule into solution, as acids tend to do, and becomes bicarbonate. And bicarbonate is how the CO2 tends to travel through your blood. So CO2 plus H2O becomes H2CO3, carbonic acid. This is the same acid you have in Coca-Cola, right? Because you're pressurizing CO2 into the water. And then if you allow that to be in fluid, generally it's going to lose a hydrogen. That's what acids do. They lose a hydrogen into solution, make the solution more acidic, and there you have hydrogen ion and a bicarbonate ion. This is what travels back to your lungs. The hydrogen ion tends to be bound up by the hemoglobin. It works as a buffer to keep your blood from becoming too acidic. And then the reverse reaction happens when this stuff gets back to your lungs. And this is a figure in your book that's a nice summary of all of this, showing you kind of what's going on around the red blood cell in terms of CO2 transport. And this is in your BioFlix or your A&P Flix on Mastering A&P. I highly recommend you watch this gas exchange video if you're having trouble with this. It's really a nice video for you to watch.